Welcome back! In this session, we'll tackle the problem of personalized headshot generation, designing a system that can take just a few casual photos of a person and transform them into professional quality headshots. This task has huge practical value. Many people need headshots for LinkedIn, resumes, company profiles, or even social media, but not everyone has access to professional photography. A well-designed system can deliver studio-quality results that are both realistic and personalized, capturing the user's unique identity while maintaining the polish of a professional portrait. But this problem is challenging. Unlike generic image generation, here we need to preserve identity. The model must capture subtle features like facial proportions, hairstyle, skin tone, and expressions, while still producing diverse, natural-looking headshots in different settings and styles. In this video, we'll start by clarifying the requirements: what input the user provides, how we handle imperfect photos, what resolution is needed, and whether we can leverage pre-trained diffusion models as a base. We'll then frame this as a personalized text-to-image task and explore different approaches: textual inversion, DreamBooth, LoRA, and tuning-free methods. Each has its own trade-offs in terms of accuracy, speed, and storage. From there, we'll walk through data preparation, model architecture and training, and the sampling process for generating studio-quality portraits. Finally, we'll discuss evaluation metrics, both offline and user-facing, and bring everything together into a full system design pipeline. By the end, you'll understand how to build a system that generates professional headshots on demand, balancing personalization, quality, and scalability. The problem is to design a system to generate headshots of specific people. Here are some good requirements to ask users would provide a few images of themselves, right? What if some images are not good? What resolution is required? Can we start from a pre-trained generic T21 model? Can users provide a text prompt? Our task is to take several images of a user's face from multiple angles and generate high-quality professional headshots of that same individual. We treat this as a personalized text-to-image generation problem, where the input is a small set of identity-specific images and the output is generated headshots. Our base is the T21 diffusion model, pre-trained on a broad and diverse dataset to capture rich visual priors. On top of this, we explore personalization techniques. 1. Tuning-based methods. Here, we fine-tune the base diffusion model for each identity using their reference images. This approach can capture fine-grained facial geometry, unique skin tones, and subtle identity cues. It is versatile, capable of personalizing for pets, products, or other objects, but requires significant computation for each new user. 2. Tuning-free methods. These use a visual encoder trained once alongside the diffusion model. For a new subject, the encoder extracts identity features and injects them into the diffusion process. Benefit: no per-user fine-tuning, instant personalization. Trade-off: may fail to capture subtle identity-specific traits like birthmarks or exact hairstyle. 3. Specific personalization techniques. Textual inversion introduces a special token that represents the user's identity in the model's vocabulary. Only the embedding for that token is learned from the reference images. The rest of the model stays frozen. Pros: extremely storage efficient, preserves the base model's knowledge, fast training. Cons: limited in capturing nuanced details. Faces may appear similar, but not exact. DreamBooth fully fine-tunes all parameters of the pre-trained diffusion model using a handful of subject-specific images, often as few as 3 to 5. Uses a rare token identifier, e.g., SKS person, to represent the subject, avoiding accidental collisions with existing tokens. Incorporates class-specific prior preservation loss. Prevents catastrophic forgetting of the general class. person still looks human in various contexts. Encourages the model to retain diversity in pose, lighting, and background. Pros: highly effective at learning distinctive identity features, works well with very few input images, and generalizes the subject to new scenes, outfits, and styles. Cons: large storage footprint for each personalized model copy, high GPU requirements, slower to onboard new identities. Low rank adaptation, LoRA, injects small trainable rank decomposition matrices into the model's attention layers and trains only these. Pros: keeps the base model intact, reduces training time, lowers memory and storage needs. Cons: slight increase in inference time and identity fidelity may be slightly less precise than full DreamBooth fine-tuning. Trade-off summary. DreamBooth: best identity fidelity, higher cost. Textual Inversion: most efficient in storage and speed, but detail capture is weaker. LoRA: balanced approach, good quality with low resource usage, tuning-free methods, instant personalization, but lower detail accuracy. By framing the task this way, we can choose the optimal method based on business constraints, whether speed of onboarding, storage limits, or identity accuracy is most important. For DreamBooth-based personalized headshot generation, the data preparation stage is critical because the quality and diversity of the training images directly affect how well the model captures the subject's unique identity while preserving the realism of a professional headshot. We start with image resizing to ensure all training images conform to the model's expected input resolution. DreamBooth models typically operate at fixed dimensions, for example, 512 by 512 pixels, so resizing ensures consistent spatial representation while maintaining aspect ratio to avoid facial distortion. Next, we use image augmentation to artificially expand the dataset. This includes small rotations, horizontal flips, slight color adjustments, and cropping. Augmentation not only helps the model generalize better, but it also reduces overfitting to the few provided reference images, a common issue in personalization tasks where only 5 to 10 images are available. Finally, we incorporate generic face data addition. This is a key step in DreamBooth training. Alongside the subject-specific images, we mix in generic face images from a broader dataset. This supports the class-specific prior preservation loss used in DreamBooth, which helps maintain the general concept of what a human face looks like, while learning the target subject's unique details. Without this, the model could overfit and generate unrealistic faces or lose the ability to produce diverse, high-quality headshots. In short, this data preparation pipeline ensures that the model has both the precision to capture the subject's identity and the flexibility to generate natural, professional-looking headshots in different contexts. In our model development phase for personalized headshot generation, the foundation is a U-Net-based diffusion model pre-trained to generate high-resolution 1024 by 1024 images. Architecture details. The U-Net has two major paths: downsampling path, a sequence of convolutional blocks that progressively reduce spatial resolution, i.e., 1024 to 512 to 256 to 128, while increasing channel depth. This path captures high-level semantic features such as facial structure, hairstyle, and background composition. Upsampling path mirrors the downsampling process, gradually restoring spatial resolution while decoding fine-grained details like eye color, skin texture, and lighting effects. Skip connections connect matching resolution layers between downsampling and upsampling, ensuring preservation of important local details and preventing over-smoothing. Cross-attention layers allow conditioning on prompt embeddings or image features, enabling the model to integrate subject-specific features into the generation process. The architecture is pre-trained on a large, diverse dataset of faces and scenes, so it already understands general facial anatomy, lighting, and style variations. Training process, diffusion model. The training is based on the denoising diffusion probabilistic model, DDPM, framework. Forward process. Starting from a clean image, x0x_0, we add Gaussian noise progressively over t time steps to produce xtxt, which is almost pure noise. Conditioning signals. For personalization, we condition on user-uploaded images combined with generic face images to maintain generalization. The user face features are extracted via a visual encoder and fed into the cross-attention layers of the UNet. Noise prediction. The model learns a function to predict the noise given the noisy image, time step, and conditioning. Loss functions. Reconstruction loss, MSE. Class-specific prior preservation loss. Maintains the model's ability to generate diverse human faces and prevents overfitting to a single identity by mixing in non-user images from the same class, e.g., portrait photo, during training. Sampling process. At inference, we reverse the diffusion process. Prompt setup. Because users don't supply text prompts, we craft a set of hand-engineered prompts, e.g., professional corporate headshot, soft lighting, blurred background, that steer generation toward clean professional aesthetics. Initialization. Start from pure Gaussian noise. Iterative denoising. The model progressively denoises xtxt down to x0x0 over tt steps. At each step, classifier-free guidance, CFG, is applied by combining unconditional and conditional predictions. This pushes the output toward images that match the user's facial features while keeping realism. Headshot personalization goals. Preserve identity-specific features such as facial proportions, hairstyle, and skin tone. Maintain photographic quality, sharp focus, balanced lighting, and natural color grading. Avoid overfitting artifacts like distorted facial features or unrealistic textures. By combining a pre-trained UNet diffusion backbone, careful conditioning, and a hybrid of identity-specific and generic data, we ensure the model produces studio-quality personalized headshots that are both faithful and aesthetically appealing. When evaluating our personalized headshot generation system, we focus on both offline and online metrics to ensure the model meets both technical quality standards and user satisfaction goals. Offline metrics allow us to assess performance without direct user involvement using automated quantitative methods. Text alignment, clip score. Even though users don't provide explicit prompts in our system, we can still measure how well-generated images align with the intended headshot description, e.g., professional headshot, neutral background, by comparing image embeddings to text embeddings from clip. Image quality, FID, inception score. FID, Fréchet inception distance, measures how close the distribution of generated images is to real professional headshot datasets. Lower is better. Inception score evaluates both quality and diversity, ensuring the model generates varied yet realistic headshots. Image alignment, clip score, dino score. Clip score here measures visual similarity between generated images and the reference user images. Dino score is a self-supervised similarity metric that captures more fine-grained visual alignment, such as facial features and structure. Online metrics measure actual user interactions and satisfaction. User feedback, direct ratings, and qualitative comments help us detect subtle issues like lighting, expression suitability, or perceived realism. Conversion rate to paid service. Tracks how often free trial users upgrade to paid plans, a strong signal that the generated results meet or exceed expectations. By combining offline metrics for technical rigor and online metrics for user value, we get a balanced view of system performance and can guide future model improvements. This slide gives a high-level view of how the entire system for personalized headshot generation comes together, from data preparation all the way to user-facing inference. Data pipeline. The first step is data preparation. We collect and pre-process two key sources of data: images with the subject of interest, i.e., the user's uploaded photos. These are typically a handful of selfies or casual photos taken from different angles. They undergo pre-processing steps like face detection, background cleanup, resizing, and augmentation to make them suitable for training. Images of generic human faces, which provide a broader foundation to help the model retain general knowledge about what a professional headshot should look like. This prevents overfitting on just a small set of user-provided images. Training pipeline. With the data prepared, we move on to personalizing a pre-trained diffusion model, like a T2IU net-based architecture. Using methods such as DreamBooth or LoRA, we adapt the model to the subject's identity while preserving its ability to generate high-quality, general human faces. Training involves the same diffusion training process, noise addition, conditioning preparation, and noise prediction, but customized with the subject's images. Inference pipeline. Once training is complete, the system enters the inference stage, which is where the user interacts with it. The image generator takes the personalized model and produces professional headshots using curated prompts and sampling strategies. The quality assessment service automatically filters out images that don't meet standards for sharpness, alignment, or realism, ensuring only high-quality headshots are presented to the user. Finally, the uploader service delivers the generated headshots back to the user in a seamless and user-friendly way, often as a batch of professional-grade portraits for selection. In short, this design ensures that the pipeline is data-driven, personalized, and user-centric, balancing technical model performance with user experience and quality control.